Hello, this is Aryan Miriyala, and this is mine and Cedric's CS4200 final project. We have decided to go with Super Mario Reinforcement Learning Agent, and I'm going to be talking a little bit about it in this video. So the contents in this presentation are going to include why we chose Super Mario and why we decided to go with this for our reinforcement learning project. We're going to be defining the environment within which Mario is going to operate, and we're going to give a little introduction about what reinforcement learning is. We're going to define the two strategies that we're going to use, called Proximal Policy Optimization and DPU Network. These are the two reinforcement learning algorithms that we're going to use. We're going to talk about the results within these two. Then we're going to talk about the challenges we have faced and if we were able to work around them or not, and what we did and how we did it. I'm going to end this with the conclusions about what we learned. So, why did we choose Super Mario? Super Mario is a very popular game and an interesting topic in the context of artificial intelligence and reinforcement learning. The dynamic environment and the dynamics within the game itself give us a ton of strategies that we have to work with, which interested me to go pursue this. The game is easily accessible through OpenAI's Gym, which is one of the other reasons why I chose to go with Super Mario. The emulators are already present and there, so we just can get it for free online through OpenAI's Gym. There have also been extensive amount of studies done on Super Mario, which help us understand things better. So let's give a short definition about the environment. Let's give Super Mario World a piece description. The performance measure is going to be for Mario to reach the end of the level. The environment is going to be the game world, the enemies, the platforms, and everything included in. The actuators are going to be the actions that are possibly taken by Mario. We are going to be restricting these actions by a lot to just save computational space and to cut down the amount of data we need. The sensors are going to be the elements that provide information about the current state, position of Mario, obstacles, and the enemies that he faces. I have to include that the action space is restricted to cut down the amount of data that we need to be processed, that we need to consume and process to train our model. I have also employed something called as grayscaling to cut down the data to be processed to 1/3. We utilize a lot of new concepts, such as wrapping our environment within different wrappers to cut down the computation size and achieve a sense of memory, and many other strategies that I'm going to be talking throughout this presentation. Super Mario in general has a huge action space and state space, and the state action pairs are going to be at an incredible number, so we have to employ methods to cut down the amount of data that we need to process. We also need to understand what learning rate is. The learning rate tells our artificial intelligence agent how important new information is compared to the old one. We are going to be taking a considerably low number to do as our learning rate, just because we want to achieve convergence for our model gradually and not completely. Grayscaling, frame stacking, resizing, and skip framing are some of the strategies that we have used to cut down computation. Now let's give a short introduction about what reinforcement learning is and what our approach is. Learning how to maximize expected rewards based on observations is what reinforcement learning does. It is just a machine learning approach to help software make better decisions. We have talked about Markov decision process before, and this is basically a Markov decision process, but in this case we have no idea what our transition probabilities are and what the reward function is. The agent explores environment within the actions provided and learns the optimal actions for a state that are to maximize reward. So the agent just tries to explore the environment and tries to understand what the actions are that are going to help it reach its final state and how to maximize its rewards. We're going to be talking about two of the most famous algorithms, the PPO, Proximal Policy Optimization, and DQN, DPU Network algorithm. Let's talk about a few strategies before we dig into the algorithms. Grayscaling. It is a strategy that helps us convert colored images to grayscales which in turn reduces the computation that we need to do. It cut down the computation size by 1/3 because all the RGB colors are now converted to gray. Skip framing is another strategy that we're going to use, and we use it to skip several frames within the environment that need to be processed. This again is to cut down the computational size and the amount of data that we need to compute to achieve convergence, and this also accelerates our training process. Now let's talk about some more strategies. Resize operation just resizes the frames that we take in, which in turn again reduces the computational data size. It just reduces the resolution of the frames, so we can use reduce the computation size again. Frame stacking is another approach that we use, so we can stack multiple frames together, which creates a sense of memory for the artificial intelligence agent, and it helps to see further, so Mario can actually see further. Dummy vector environment. This helps us with vectorizing the environment, which helps us run several copies in parallel. This is again done to cut down the computation size. Why talk about these concepts? The computations that we're going to be performing are going to be very high because of the sheer amount of state action pairs. So we're going to have to employ resources that help us cut down the computation size without affecting the quality of the data. And these whole strategies help us with doing exactly that. Even with this, running a training model is extremely difficult, and we're going to be talking about that. The CNN policy, the convoluted neural network. This is a specialized neural network architecture used for analyzing visual data, which is what we're doing this time. A video game can be considered as a stack of frames together that needs to be visualized for our agent. We utilize something called as convoluted layers and linear layers within the environment, and this helps the agent to understand the environment and the hurdles and the enemies and the positions. The policy automatically extracts raw data from visual input, and it is very helpful for interpreting frames, image frames, especially in cases where we're doing game agents. And why we're using CNN policy for a Mario agent? We are going to process the environment as a stack of frames or images that contain raw data for the agent. So a video game can be visualized as a stack of frames, and this is what is happening exactly with Mario environment. The CNN policy analyzes the game screens to recognize important elements, such as the position of Mario, the position of the obstacles, and everything else. And this policy helps us with predicting optimal actions based purely on raw data from visual inputs, which is great because that is what we're trying to do here. The CNN policy with reinforcement learning algorithms help our agent understand optimal actions. The policy is continuously updated because of this, so it helps with going to convergence faster. Now let's talk about PPO, the Proximal Policy Optimization algorithm. This is a reinforcement learning algorithm that trains agents to perform tasks where the future states are dependent on the actions that we perform and the rewards that we get. Focusing on optimizing the policy function mapping observed states to relevant actions. So we focus on trying to optimize the policy function, and we try to map the observed states to relevant actions in the policies. We have iterative updates so that the agent is learning to make better decisions, optimizing over time. PPO algorithm is better for stability and efficiency within the neural networks because of the small step size that we take, which helps with gradual reach of the convergence. We also employ something called as a clipping mechanism that limits the change in policy during each update, so we don't jump onto high changes really fast. Let's do a short demonstration on code. Now, before we do anything, we have to make sure that we go to how to read README. This tells us all the libraries that we need before doing anything. We have to also create a virtual environment and also activate that virtual environment before we do anything. This is exactly what I'm doing here. I have activated my virtual environment with this already. And once we do that, let's go to DQN and talk or PPO and talk about what we're doing here. These are all the libraries that we're going to be using. Stable baselines is where we're going to get our PPO algorithm from. This is written by OpenAI. And we're also importing the Super Mario Gym because that is what we're going to be using here. And we're going to import our wrappers. If this is the first time that you're training the algorithm, you're going to have to set should train to true and should test to false. But because I have already trained my algorithm and I have models ready, I don't need to do that. Now, this is where these are all the functions and classes that deal with training and logging. So every time you run this, we're going to be training our algorithms. We're going to be putting the log into the logs directory, which are going to give us a bunch of graphs which help us understand how our data is moving, and the model itself is going to be put into train directory. Now the callback, we're calling back the train and logging function, which is this. The check frequency gives it how many step sizes that it needs to take before creating a new model. I am restricting my total step count to 100,000, and we're going to explain this later. We see that the should train is set to false, so we're not going to go there, but should test is set to true, so we're going to go there. Now that I have all of that, let's run the algorithm. So this is the Mario environment and the Mario agent running by using the PPO algorithm. We see that he doesn't perform super well because we only use 100,000 total step count, which is not ideal for achieving convergence. We need at least a minimum of 4 million total step counts before we reach convergence, but I was not able to do that because of the sheer amount of resources that it takes. The computers that we use are not as powerful as compared to other people that have done it before, so we just could not have our computers run such high computations. I'm going to stop the demonstration here just to save some time on our presentation. Now let's go back to our presentation. So that was the PPO algorithm running with a trained model at 100,000 step size. The model could not finish the level just because of how much data it needed to do compute. Now these are some of the things that you're going to see when you're training your model, and these are two consecutive iterations. We see that the two most important things that we're going to be looking at is the loss, and we want the loss to go down with each iteration, and we want the entropy loss to go up with each iteration, which we see is the case in our slide. Now let's look at some of the graphs. Now this is a graph for episode rewards mean, and we see that the graph goes up and down, which is a good indication because that means each episode, the way we define it, the reward function goes up and down, which means Mario is learning new stuff and is able to employ that new stuff, and he keeps learning to optimize his actions for each state. Let's look at the value loss. This is the value I was talking about before. We want the value loss to go down, which we see is the case, and this is the entropy loss, which we want to go up, which we see the case. These two together imply that our model is going close to convergence. Some of the challenges that we faced is not having enough computational power and resources to train such a big model. Based on my research, we need at least 4 million total steps to achieve convergence, which is just not possible with the computers we have. Running it for such computation is just not possible. And the best we were able to do was 100,000 step size, after which the reward function breaks and acts weird. So this is where we decided to stop. Now let's go to DQN, the Deep Q network. It's a variant of Q learning algorithm and is popular reinforcement learning algorithm. It uses the CNN policy to approximate Q functions. Experiences are stored in a replay buffer and updates are made to the Q network accordingly. Stability is improved by something called a target network, which is a copy of the Q network, and we update this based on the values we get from Q network. let's go for another short demonstration of code. We do the exact, this is the PPO DQN file, and we're using the exact same libraries and we're doing the exact same strategies. We are going to have to follow the same things for training. And now that I already have my DQN models trained, so I'm going to use those. I'm going to use the 200,000 size here. Now let's run the DQN file. So we see that Mario is running with the DQN algorithm, and he knows, a good indication is that he knows when to jump. He knows that he needs to avoid enemies. When he sees enemies he needs to jump. He goes through the hurdles by jumping through on the pipes. Every time he sees a pit, he jumps, which are all good indications. Unfortunately, we were not able to get our model to converge just because of the sheer amount of computation we need. It is said for my research, I need at least 50,000 iterations, which is just not possible. The best I could do was 200,000 iterations, which translates roughly to around 7,000 to 8,000 iterations. So I'm going to stop this just to save some time. As you see, the total time steps I did was 100,000. I did 200,000 before, which translates roughly to around 8,000 iterations, but I'm going to need at least 50,000 iterations to achieve convergence. Let's go back to our presentation. Now we're going to be talking about some more graphs. This is the episode rewards for DQN algorithm, and we see that the reward function is going up and down, which is a good indication, which means that Mario is learning something new every episode. This is the exploration rate function, and we see that it gets stable after a point, which should be because it is getting to convergence, but convergence does not mean optimal values, which is what the case we've seen. The challengers are similar to the PPO algorithm. We just don't have the computation power and resources to run such a huge model. The model converges to an optimal value after 50,000 iterations, which is just not possible to do with the computers we have. I was able to do, as I said, 200,000 total time steps, which is roughly around 8,000 iterations. So let's talk about the conclusions and the lessons learned. Theoretically, DQN is supposed to perform better than PPO, and we see that that's the case in our algorithm, in our project as well. DQN does perform better than PPO, just because of the exploration and the way it's been designed. DQN algorithm takes necessary actions and it does it more accurately than PPO in general. Although we were not able to use the upper limits of training because we don't have the resources, it has been true in general. Another important thing is the wrapper strategies. Using the wrappers helped us out immensely with reducing the amount of data that we needed to process, especially grayscaling and frame sizing. Frame stacking is another important wrapper that helps us to achieve a memory-like feature for Mario Agent. Overall, we have learned numerous concepts about reinforcement learning and how to evaluate rewards. The reward function for Mario is extremely concept because of how many things he's doing at any time. It was designed by the writers of PPO and DQN, which are by the people that wrote the OpenAI. OpenAI owns PPO and DQN, so that is who designed the reward function. We had no control over it. Both the algorithms do a very good job at trying to achieve convergence, with DQN being better overall. And that has been confirmed by our project as well. Thank you for listening.